This is Chapter 1, Geologic Time, Sections 12-1 and 12-2. So we're going to just talk about a little bit about what geologic time is and how it relates to Earth's history. So, Earth's history is a sequence of geologic events. Rocks, in particular, sedimentary rocks, represent passage of time. They're being deposited over periods of time, so those rocks actually represent time. There are 5 geologic events used for relative age dating. Relative age dating does not give you a number, it just says that these rocks are older than these rocks. So you won't get an actual number. And so the 5 geologic events are deposition. Rocks are being deposited, and as I said, they're being deposited over a sequence of time. So those rocks that are being deposited, those sediments being deposited, actually represent time. Erosion. Erosion removes those rocks and breaks them down. So the erosion actually removes geologic history from the rock record. Intrusions. Intrusions cut into rocks. You can use them to date whether they're older or younger. Faulting works the same way, which we're going to talk a little bit more in a couple of sections. Faulting works the same way. The faults move the rocks, so the rocks had to exist in order to be moved by the fault. Deformation and uplift. Same thing, deformation, rocks are being deformed and uplifted. They had to be present in order to be deformed and uplifted. Otherwise, they would not have been deformed and uplifted. So these are the main geologic events that are used in relative age dating. So when we look at this picture, this is an igneous intrusion. I know that this igneous intrusion is younger than the surrounding rocks. And that's all relative age dating is. You're using a set of common sense principles to figure out how old rocks are relative to each other. And students, when you get this, it's super easy. You love it. There's no math involved. Same thing here. Here's a fault running through this system. All these rocks that are present and that have been moved by this fault are younger than the fault. Otherwise, they wouldn't have been moved by the fault. And here's a fold. So once again, these rocks had to be present in order to be deformed by the folding. Okay, so now we're going to talk about section 12-2. And really, there's 2 ways to date rocks and geologic events. Relative age dating, rock ages relative to each other, which one is older. And then the second one is radiometric or numerical age dating. This is when you calculate a number or calculate an age. So you'll actually get a number. And it's using radiometric isotopes. So when you look at geologic time, geologists analyze and interpret evidence gleaned from the rock record. So you're analyzing the information using relative age dating and using that to interpret what has happened, the order of events. And so the rock record is the record of Earth's history preserved in the crust. Okay, so dating, as I said, you'll use relative age dating, and you're going to be using common sense principles in order to figure out the order. So you will figure out the chronological sequence. Chronological just means time. And then you have your radiometric dating, which uses decay of radioactive isotopes within minerals to calculate the chronological age. So in general, you use a combination of relative age dating and radiometric age dating because this is done on metamorphic and igneous rocks primarily. The reason being, sedimentary rocks are usually not radiometrically dated for two reasons. One is they do not contain the correct chemistry, so they don't have the radioisotopes in them. And two, if it is a clastic sedimentary rock, you will get the age the parent rock formed, not the sedimentary rock. So what that means is the age of classic sedimentary rocks are always older than what they're being dated to, because when you date them, if they contain the correct chemistry, you're dating the igneous or metamorphic rock that it formed from. So you're not getting the age the sedimentary rock formed, you're getting the age of the original parent rock. So classic sedimentary rocks are always older, their dates are always older than what they formed because you're not dating the right thing. So sedimentary rocks usually do not contain the correct chemistry. If they do, and they're a chemical sedimentary rock, you can date them, but usually they don't contain the correct chemistry. And if they're classic sedimentary rock, you'll get an age that's much older. So I'm going to show you a couple of pictures of the geologic timescale. This is actually from chapter 13. This is figure 13.7. So this is the geologic timescale. So you have the Precambrian and Phanerozoic. The Precambrian is not an official term because it's broken down from eons, eras, periods, and then epochs. So the largest period of time is your eon. Then you have your eras. Then you have your periods. Then you have your epochs. So eons a large period of time, epochs are the shortest period of time. So you have 4 eons. You have the Hadean, Archean, Proterozoic, and the Phanerozoic. Then the Precambrian and the eons are broken down into eras, but no one knows them because very few people actually work in the Precambrian. Even though it encompasses 88% of geologic history, it's still, there's not that many Precambrian rocks. They're highly metamorphosed, so very little information can be found. Most of the fossils found there are soft-bodied organisms, so you don't get very many fossils either. Then you move into the Phanerozoic eon, which has 3 periods, the Paleozoic, the Mesozoic, and the Cenozoic. Then Paleozoic has the periods Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. If you are not in the United States, you call the Mississippian, Pennsylvanian the Carboniferous. The Mississippi and the Pennsylvanian are two periods in the Paleozoic that are very well known, and we have great rock records from them here in the United States, but everywhere else in the world they do not have very good Carboniferous records, so they just dump it all into the Carboniferous, but here we separate into the Mississippi and the Pennsylvanian because we have really good rocks of those ages. Then you have the Mesozoic, which is your age of dinosaurs, the Triassic, Jurassic, and Cretaceous. Then the Cenozoic. They were originally broken down into tertiary and quaternary, but they are no longer, those are antiquated terms. They're no longer really used, but for some reason textbooks still drill them in. The Paleogene, Neogene, and the quaternary are used more often. So that's why these terms are, because these replace the tertiary. And then you have epochs. You do have epochs for all your Paleozoic and Mesozoic, but the epochs for the Cenozoic are much more known because the closer you get to modern day, the better the fossil record is and the better we can geologically and radiometrically and relatively age date the rocks because there's more of them around, because they're closer to the surface. So that's what the epochs are. There's also another really good figure in Chapter 13, 13.29, which we're not really going to go over major events in geologic time. If you're interested, recommend reading Chapter 13. It's a great chapter. We just don't have time. But so it goes from the Hadean, which is when the Earth formed, to Archean, to the Proterozoic, then into the Phanerozoic, Paleozoic, Mesozoic, and Cenozoic. And so these are just showing you major events that happened. So here, you're showing you what the continents look like, what mountain belts were forming, early plate tectonics. Down here you start looking at evolution. So archaea, bactericide, these are the first organisms. They appeared about 3.5 billion years ago, and the Earth is dated to 4.5 billion years. So you can see where life is and then how it spreads out through geologic time. So this is just a really good pictorial representation of geologic time.